All right, so let's get started. So we will have our midterm next week, so at the same time, and it will be a closed book midterm exam, and the coverage will be from lecture 1 to lecture 3, so to the memory management part, and we will not cover the advanced topics. So the advanced topics I will mark like this is advanced, like one moment. Like here, there are all advanced topics. So they will not be in your midterm. And then, and because we have a little bit too many of folks here, so like we will split you into 2 rooms. So one will be in the EC building and one will be here. So we will announce the seat table this week. And we'll also announce our second hands-on on October 28th in 2 weeks. Okay, so like the form for the midterm exam, I think you guys can find most of the resources in the internet. They will be very similar to you can see find in the internet. Okay, so questions. All right. So let's first do some Q&A, and then we'll do some recall. Oh, one more thing is actually today's all of the contents today were not included in your midterm, but excluding the recall. I mean, recall is for last week, so it sure will be in your midterm, but for the advanced topics and then for the storage device, it will not. Okay. Okay, so Q&A. The first one is when a file packet file is mapped into virtual memory, if the file is modified, will the mapped region be automatically updated? And the answer is yes. So actually all the update will be synced with the file on the storage device. Okay, so the second one is like the relation between virtual address space and memory fragmentation. I think this is a good question. And the answer will be like, actually, the virtual address space, I mean, the design goal for the virtual address space is not going to alleviate or like remove the memory fragmentation. The virtual address space is designed for making each process has their own consistent, isolated, and flexible memory view. So it makes the programmer easier to do the programming. The programmer doesn't really need to care about the other programmers, how they use the memory. So this is virtual memory. And the thing like it can really solve the memory fragmentation would be the physical memory allocation. So it includes like patch frame, and then it includes like body systems or even like the slab allocation. They are all possible to deal with the memory fragmentations. Okay. So another question is about why MM structure only records the number of threads and process. There are detailed information about threads and process stored. So actually the detailed information about threads and process, they are stored in the text dash structure, data structure. So usually people call them PCB. Okay, so actually structure, the only records about how many kind of process and threads they are used in this mmap structure. Okay. So there is a question is about, given some cases like where accessing a VMA is illegal. So here are the 3. I mean, there are more, but I just put 3 here. So the first one is a process access outside memory boundary. So like if the process access like the kernel memory or like the process access the memory, it doesn't kind of belong to this process. They're all for the memory outside the memory boundary. So there's the second case is about a process access read-only virtual memory with the write operations. Okay, so it is kind of the permission like error here. So VMA will become illegal. And there's a third case is about a process access unallocated or free memory. So it is also illegal. Okay, so in most cases when there is illegal, then there is a patch fault usually, and then kernel will come to deal with these illegal things. Okay. So the fourth question is about in the following scenario, when we said, oh, actually these slides, they're from our last week slides. So it is on page, I think it's 23, and we are explaining about the users and counts, what's the meaning for these two fields or like the factors. And we give you an example to say like, hey, if process one has 5 threads and you have blah, blah, blah scenario. And the question is about, we say process one has 5 threads, but actually the users is 5. And the reason is because when we say process one has 5 threads, it means process one itself is 1 thread and it has 4 user threads. So the total will be 5. Okay. So process one itself is also, it will be recognized as 1 thread in Linux. Okay. So this is also the reason why I said in Linux, it doesn't really matter about it as a process, because the key difference is about the capability to access the resource, just like what kind of resource they are isolated for process, but they are shared between threads. It's much about this kind of things. And the fifth question, I think this is not a question because there are a lot of questions related to this one. So I just summarize and then do a clarification. So a VMA is mapped to non-continuous patch frames via the patch table. Okay, so when we say there is a VMA region, it means like there is a continuous virtual address region there. I mean, it is comprised by a lot of continuous patch. Okay, but it doesn't mean the physical address or like the physical patch frames should be continuous, right? Because you have patch table. So for example, you have 10 pages that are continuous on the virtual memory address space, but it doesn't mean those patch be mapped to the continuous physical address. Okay, they can be mapped to non-continuous physical address. Okay, so this is also the reason why we are going to use virtual memory, because it doesn't really need to always use the physical address like in a continuous way. Okay. So the next one is in 64-bit systems, are the remaining 16 bits completely wasted? Oh, let me give you a little bit about the background about this question. Because we say like in 64-bit system, we only use 48 bits, right? So people are thinking about maybe there are 16 bits that are wasted. But I would say it doesn't really like it wasted, because come to think about, if you use those extra 16 bits to store some things, and your patch table will grow to like 5th layer or 6 layers. So each time you need to pay extra translation overhead there. So in current Linux, the reason they use 48 bits instead of more is because you can save more translation time. Okay, so because currently there's only 48 bits, so there are 4 levels. But if you increase to like 54, something like those kind of bits, then maybe you need 5 level or like 6 level. So each time when you increase 1 level, it means for most of the instruction, when the CPU is going to access the instruction, CPU needs to translate 1 more level. So probably CPU need to access memory 1 more. So from 4 times to 5 times to 6 times, then overhead will be super huge. So this is the reason, like, actually I will not say the 16-bit is completely wasted, but also the truth is like those 16 bits are not used in current systems. Okay, I mean it is possible to be used. I mean if you code in the kernel, it is possible to store more things, but you need to pay more overhead there. Okay, so I think the 7th one is quite interesting and important. Would the number of patch table level affect TOB heap rate? So now we use 4-level patch table mapping, right? And it is possible, as I say, it is possible if you are going to use more, and then you can use like 54 bits or like 64 bits, then you will have more labels. But what's the impact for the using more labels? So actually, things like this, actually TOB is a place to cache the translation result. So if you are going to remove the overhead for traversing the patch table, then you need to store more translation resource in TOB. But the size of TOB is fixed. So you can choose to store or like to cache the translation resource of the very first level or like the very last level. Okay, so you can think about, maybe I can have one figure here is easier for you guys to understand. So like this, it is possible for you to directly store the translation for this one. Like you only store the translation resource from this like 9 bits translation to this address, and you use TOB to store it. And the good thing is actually, because this is on the first level, so in most cases, most of the address, they will have very similar, I would say that they will have the same PGD offset, right? Because from the PGD offset to the patch offsets, there are still like 27 bits here to represent different address. So if you cache the first level, then it means like for most of the translation results, you can find them in the TOB. This is a good thing. So you can increase the TOB hit. Okay, but the bad thing is you still need to work the following 3 labels. You only finish the first label translation, right? So you still need to work the next 3 labels. So there's another way is you can directly cache the last label. What I mean cache the last label is here. You can directly store the translation from this address to this address. It is also possible. Then if there is a hit in a TOB, then you don't really need to do any translation result because you already store the 4 label translation results in the TOB. But the overhead is actually there's only one possible to hit it. I mean, you need to match the you need to match the full 64 bits address to do the TOB translation. So if you hit, then you can set 4 TOB walk. Sorry, 4 patch table walks. But if you not hit any bits here, then you need to do the patch table walking. So actually, this is the decision making between like which layer you are going to store in the TOB. Given the same TOB size, you can choose to store the first level or you can choose to store the last level. Okay. And then, all right, here. So the add one will be like, will a patch fault occur while traversing a multi-level patch table? Definitely yes. The reason is multi-level patch table, in most cases, they are located there, placed on the DRAM, right? We need some place to store this patch table. And this patch table, in most cases, they are stored in the DRAM. But the case is like the patch table is too huge. So in most cases, we will use daemon paging. I mean, like when we need one patch table and it is not in the memory, we will do a patch fault, and then the patch fault handler will move from the storage device to the memory. So they're all the same thing like when you are accessing the data. Because you can image like each patch table just like the data. Each patch table entry is just like a data, no matter it is in the memory or it is in the storage. So it just works like a patch fault that you learned before. So given some scenarios where the kernel needs to manually walk patch table, this is also very good question because last week when we were talking about patch table walking, I mean this one, when we were talking about this one, actually our starting point is the CPU walks the patch table automatically. So when we're talking this slides, actually there is no kernel involved here. I mean, operating system kernel doesn't do anything when the CPU walks the patch table, because each time CPU just access the DRAM and then do some very simple computation and then access another DRAM, I mean locations, and then get the next level, and then we access the third place in the DRAM and we get the. So it doesn't really need the help from operating system. Okay, but the case is there any examples like kernel needs to manually walk the patch table? And there are some. The first of all is like adjusting mmap region. because when we're talking about mmap region, it is also virtual address, right? We need to know where is the physical address. So we need to work the patch table by the kernel. Okay, so kernel will do a lot. Actually, there are some supported kernel function that can help to work the patch table. And actually, the concept is very similar to this one. The different thing is like, actually in the kernel, you will see there's a function called pgd-offset, pud-offset here like this. So those are you can find in the kernel. They are all kernel functions. And the reason I put here is just about to that you better understand, actually there are some things happens here. But when CPU automatically does these kind of things, it doesn't really call any function here. It just finish it by the circuit. It just finished by the hardware. Okay, so you can think about the pgd-offset here. It can be implemented by hardware circuits, or you can use the software code, the C code, to implement these pgd-offset things, because they are quite easy, quite simple. They're just going to concatenate two address together. Okay, so the first one is adjusting memory map region, and the second one is the process creations. Because when we are going to create a process, as you know, like current system use copy on write. So for copy on write, actually we don't want to copy out the new patch table. We only copy out when the patch table is updated. But the case is how the system knows the patch table is updated, right? So the kernel will first set those patch table to read only. But to set the read only flag, kernel needs to find where is the patch table. So kernel should go to work the patch table by its own, and then to set up the read only flag for those patch table related to the parent process. So in this case, after the child process created, and if someone, I mean, either the parent or the child access those patch table, then it will trigger the patch fault when they are going to write the data into the read-only patch table. Okay. And the third one, I think is quite simple, just like changing patch protections rule. For example, if you are going to change it to the write protection or something like that, I think this is quite similar to the process creation things. Okay, just like to change the permission for those patches. Okay, so the last one is, if the base address of each of it, PGD, PUD, PND, those are all patch table, are all stored in physical address space? I would say yes, especially for the last two, PUD and PMD, they are all on the physical address space, or like they are all on the DRAM, right? But the base address of PGD, it can either be in a MM structure or in a CR3 register, because we need some way to get the PGD address, not from the patch table itself, but by like if it is placed in the CPU, then we need one register to store it, or like maybe we can put it in a data structure, because each process has their own MM structure, right? So there is a field called PGD like field, and you can get the base address from the MM structure. So actually there are two places for you to get the PGD base address. Okay, but the rest of the PUD, PMD, you can get those in the patch table. I mean, you can get those base address from the PGD's patch table. Okay, so those are the questions like I summarized out, and I think they are all kind of interesting, so I let you know here. So let's then quickly do some recalls. So last week we talked about the virtual address space, and we say like each process is given a unique and flat. And unique and flat, just like the definition, they're all here. Okay, so I'll just skip it. And then the memory address is a particular value identify a specific byte in a process address space, because now we are using the byte addressable, so the address kind of granularity will be in a byte for memory. Okay, so you can see like we use 32-bit address space, but we can represent 2 to the 32 byte, not bit, because each bit we can address in a byte label. So this is byte addressable. Okay, so this is quite important, because if there is no byte addressable, then 32-bit only can address 2 to 32 bits. Okay, so it will be quite small here. So we also give you an example. If you write a C code, it is quite simple here. Just like here is the code, and then how to map those kind of things on the virtual address space. So the top kind of 1 GB, they are all for kernel. So no matter which process, they are sharing the same top 1 GB, and they are all for the kernel. Okay, only the bottom 3 GB in the 32-bit systems, they are used by the user process. So first of all, like the text section is just like the program. So the C code will be placed in the text sections, data section, BSS sections, they are all for global variable. The difference is initialized or not. So data section is those initialized global variable, and BSS are those uninitialized, okay? And then we have user stack. So inside the main function, actually for the function, for the local function, they're all be pushed into the stack. Okay, so in the main function, like you can push the variable into the stack for using them. Okay, so the second one would be like the heap, and the heap will grow from the BSS section and then to above. So the reason why heap can grow from here is because actually global variable, after you program in the C code, how many global variable you can count it. I mean, they are fixed, they are static. The number of global variable will not change. So where the global variable will stop, it can be predicted by the compiler. So heap can start, I mean, the heap area can start right above the BSS sections. Okay, so heap just like the memory allocation function here. Like if you are going to have like 20 bits, something like that, then you can use a heap to grow the dynamic memory part. And the last one is a shared library. So you can imagine like if you are a programmer and you write several C codes, actually you use a same standard IO library, right? So those standard IO library, they are stored in this area. So you can also think about if there is another C code and it also uses standard IO library, then they have different virtual address space, right? Because they are different process, but they are mapped to the same physical address. They are stored in this shared library. Okay, so you only need one standard IO library in your systems, placed in some places, but you can map to several processes. I mean, all the processes there is standard IO library, they can share this library. Okay, so this is for the virtual address space. So the next one is about the memory area structures. So it describes a single memory area over a continuous interval in a given virtual address space. So like this, actually this is the structure. So structure is just like a memory descriptor. So each process has their own memory descriptor. So inside the process, actually there are several VMA region. So for each VMA region, actually you will use one VM area structure to describe this region. So VM-area structure list is a data structure. And here is the space managed by this structure. So like this is a process virtual address space. It is like 4 GB for 32-bit systems. And like here is, you can think about maybe this is a heap, maybe this is stack, and maybe this is global memory, like those kind of things. Sorry, global variable. And this VMA is able to locate where the virtual memory is. So this is the starting point of this VMA area and the endpoint. And each VM area structure can be linked by the linked list. So they're using the VM-next to access the next one. Okay, so for the data structure wide, they're all chained together. But in the virtual address space, I mean, in terms of the space, they are not chained together. Okay. So maybe it is a little bit hard to image. So let me go back to our original process virtual address space. So this is the virtual address space that you already know, right? And then, oh, I think there's one thing is actually for heap or like for stack, no matter what it is in this virtual address space, the minimum granularity will be a patch. Okay. What I mean for minimum granularity is they're all aligned to the patch size. So the heap, if the heap grows, then each time it grows at 1, 2, or maybe 3 patch it will not be like half of the patch. Okay, so no matter which part they are, they should be aligned with the patch. So for the text section, if it is not possible to fit in one like patch area, like 4 kilobyte, and the system should still allocate the 4 kilobyte to these text sections. Okay, no matter it is not fit or not, we should go to give it in the multiple of the 4 kilobyte area. Okay, so actually for the anonymous part, like heap and BSS, those kind of non-file packet things, we call them anonymous. Okay, so actually for each process, like each process, they are described by the text data structure, right? So each process has a data structure, has their own memory descriptor. And for each memory descriptor, they are going to manage several memory area structure. Okay, because like you can think about the simple thing is this is one area structure, this is another, the third one, 4, 5, and 6. So at least there are 6. Okay, so this is the most simple way. But actually, because the heap and stack will grow, and maybe the BSS section is quite huge because maybe it uses a lot of global variable. So we need this kind of data structure to manage how large it is. Okay, like this. So for the text section, actually, we are going to use the VM-start and VM-end to boundary what's the size of the text section. Is it 1 page, 2 pages, or like if there are 4 pages? So in this case, we are going to know if how many pages they are. And then the thing is, actually, we can have several flags to differentiate different region. So actually, for the text region, we should have it for the read-only, right? Because you will not modify your code online. And because it is a text section, so it should be in an executable file because you are going to run this binary, so it should be executable. And we are going to get, okay, so where is the, where is the file? So the file is using this pointer to point to the path for this file. So it is stored on this /binary/execute folder, and you can go to execute it. Okay, so actually, when you are looking into the code, if I remember correctly, actually there is no this kind of, oh, this is the text section. So in this VMA area structure, there is a field coded text section. And there's a field called BSS. Actually, no, there is no this kind of description to say this is a text section, that is a stack. The reason is actually the difference between those kind of structure or like those text section, data section, those kind of things. The important thing is what is the permission? And then is there a packet file? These kind of things. I mean, Linux doesn't really need to differentiate. This is a heap, or that is a stack, or this is a text section. Okay, because with this kind of permission and with this kind of file, packet file, actually it is well enough for Linux to manage this area. Okay. So you can also think about it is because it will let you easier to understand how virtual address space look like. So people are going to give them several names about, hey, this is a stack, this is a heap. But for Linux itself, actually, it's just about a lot of logistic behind those heap and stack. Okay. So for the data section, we use the same things like the text sections. Okay. And the difference is because actually for data sections, like it can support the write. So it doesn't really need to be read-only. And data section is not executable because they are old data. So they are not executable file. Okay. So this is for data section. But the thing is, because they are all initialized data, so we need to get what is the initial value. So we need to get it from the executable file. Okay, we need to get it from some place. So for the BSS, actually, it doesn't really need to be a file packet because those variables, they are not initialized in your code. So it doesn't really need to know what's the value in the code. Okay, because they are all initialized online. Okay, so here comes a like VM area structure. So this is for heap. So because heap grows dynamically, so it doesn't really know how large it is. It should be decided when you are running, and it keeps growing. So in most cases, the virtual address should not be, I mean, the height, it will be not continuous in most cases. So in this case, there will chain for a long, like for example, maybe these three, they are all related to the heap. So this is the first heap, second heap, the third heap. They're all chained together by these data structures. And then they point to different like physical address, like these kind of things. Okay. So for the memory mapping for shared library, actually it should be file package because we are going to know whether it's the the shared object file. So in a Linux. And for the stack, actually the stack and the heap, it looks very similar. The different thing is for the stack, it can grow down. It should grow down. So stack function should grow down and heap will grow up. So for this tag, it will be VM dash grows down to know, hey, actually this is a stack. Okay, so this is the relationship between the virtual memory area and the virtual address space you learn in the undergraduate. Okay. Okay, so hash table. So hash table just like it is going to like a book that record the translation result between the virtual and physical. Okay. So with this hash table, you can translate the virtual address to the physical address. So it takes responsibility for address translation, and each process has their own patch table. And for all the threads, actually they share the patch tables with their parent process. Okay, so for threads, they have no patch tables. I mean, they have not their own patch table. So each patch table comprises a bunch of add byte patch table entries on 64-bit systems. And the size of patch table is proportional to the memory size. I mean, the more memory you use, the larger the patch table it is, because each 4 KB patch, usually you need one patch table entry to locate where it is. Okay. So Linux use the multi-level patch tables, and now we only use 48 bits out of the 64 bits, so there are 4 levels. So in most cases, when CPU is running the instructions, they're going to fetch your data, those kind of things. CPU should first work a patch table to get where the data is. So CPU will run, or I should say, CPU will traverse the patch table automatically. And TLB is a hardware cache to keep the mapping between the virtual and physical in the CPU. Okay. And there are 2 kinds of patch faults. One is minor and the other is major patch fault. And the key difference is for major patch fault, it will involve the IO movement for major patch fault. So major patch fault is the things you learn in your undergraduate. The data will be moved from the store device or like the network device, IO device to the memory. And minor patch fault, they will not involve IO movement here. So usually it is about the MMU is not really ready for serving this kind of, or I should put like this. The patch is already in the memory, but it is not marked. For example, maybe the entry is not set it, and maybe when we are using the memory allocations, and if you are going to allocate a super huge region, but your code doesn't really use that much of memory, so those memory will not be, the address translation for those memory will not be set up when you do the allocations. So it will be set up when your code access those edge region. So this is what I say, like once being touched by your program. So how the CPU works patch tables? I will quickly go through this because that's why we already did it twice. So this is a 64-bit systems, and actually the first few bits here, they are unused. There are 16 bits, they are unused. And there are 4 labels for PGD, PUD, PMD, and patch table. So you have 4 level patch table working. And the last one, the patch offset is for the system to locate the data inside a patch, right? So each patch is 4 kilobyte. So if we are going to get the exact address inside the patch, we need this 12-bit. This 12-bit can address inside a patch. So you can think about PGD, PUD, PMD, and patch table. The four combined together, you can get where the patch is. And then if you are going to know more about, hey, I'm to get like the first like 1 kilobyte inside this patch, then you need to use this patch offset to get it. And the base address of the PGD is maintained in CR3. So when the CPU is going to do the translation, actually CPU will only get this one, the virtual address space here, and the register is already in the CPU. So CPU know where is the base address for the PGD. Okay. So with this base address is always point to the bottom of the first table of the patch table. Okay. So for this patch table, actually it stores in 4 kilobyte patch frames. Okay. And each PGD entry is 8 byte. So 4 kilobyte divided by 8 byte, there are 512 PGD inside. And we are going to know which PGD entry is it. So we will use this PGD offset to know where is the PGD entry that we are requiring for. And for this PGD entry, actually, we can get the next label's bottom. So this PGD entry will point to the next label, the patch upper derivative PUD table here. And you can think about like PGD entry, this one will point to another patch frame, and this patch frame is also belonging to this patch upper derivative table. So for the patch upper derivative table, there are more. Maybe there are 512 of the patches there. Okay. So we do the same thing because we are going to know where the entry that we are going to get. So we use a PUD offset to locate the PUD entry inside the patch. So with this PUD entry, we can get the next label, and it iterates. They're the same things, okay, until the last label. Because the last label, actually, when you read out the last label, the layout like this, we say like each entry is 8 bytes, so there are 64 bits, and the first 12 bits, actually in the last label, there will be control bits. So control bits including the present bit, 30 bits, those kind of things, they are for control bits. They are still unused. So these 16 bits, they are unused. And between the 12 bits and 48 bits here, it is the physical address. Okay. But this physical address only point to the patch. So if you are going to know the exact address inside the patch, you are going to concatenate this patch offset with this control bit. Okay. So what MMU usually do is like this. MMU will concatenate the offset to here. It will replace the first 12 bits and then do the concatenation together. So it is quite simple circuit here, just like to concatenate two things together. And you can get a 48 bits physical address. Then we are finished the translation. Okay. So this is for the patch table working. Okay. And the next question is about like why it is 4 label. I mean, is it possible to be like 3 labels, or like is it possible to go it up to 5 labels? The reason for 4 label is because the assumption in current Linux is the regular page size is 4 kilobyte. So there are 2 to the 12 bytes. And the virtual address space size is 48 bits. So we use 2 to the 48 bytes. Okay. And the patch table entry size is 8 bytes, because there are 64 bits here. So we use 8 bytes. Okay. So with this kind of spec here, it is possible to calculate how many labels that we are using. So the key thing for doing this calculation is for the first label, it should be, I mean, for all the entries belonging to the first label, it should be inside one patch. Otherwise, the PGD cannot get the right patch for you, because PGD can only point to the base address, and there's only one patch can be point. So the first label, for example, like this, if your first label, there are 2 patches here, then you only have 1 PGD, then you cannot get to the correct patch, right? So if your first level, there are 2 patches. You need 2 PGD base address, or you can think about you need 2 CL3 register. So if there are 3 patches for the first level, then you need 3 CL3 registers. But current CPU, current Intel CPU or AMD CPU, ARM CPU, they only support 1 PGD base address in most cases. So the first level should be fitting 1 patch. Okay. So let's do the calculation. So we are going to calculate how many patch table entries there are. So for the last level, like we say we have 2 to the 48 virtual address space. So we divide by the 2 to the 12 patch size. And then we can know we have like 2 to the 36 patches here. So for each patch, we need 8 bytes. So the size of the patch table entry total will get 2 to the 36 times 2 to the 3, so 2 to the 39 bytes. But 2 to the 39 byte is larger than 1 patch, because our goal is to let all the patch table entries for this level to fit in only 1 patch. And 1 patch is 2 to the 12, like this, the patch size here. So 2 to the 39 is larger. So we have a lot of patches to store this amount of patch table entries, okay? So it is not possible to fit. So we need the next level, okay? So to fit all this to the next level, the calculation will be like 2 to the 39 divided by 2 to the 12, because we need to store those patch table entries inside the patch table. Sorry, inside the patches, okay? So 2 to the 39 divided by 2 to the 12, and then times 2 to the 3, because we are going to know the total amount of the patch table entries here we are going to use. So for this one, we will get 2 to the 30 byte. So it's here. This here is 2 to the 30 byte. 2 to the 30 byte is still larger than 2 to the 12 byte. So we need another level, and then you repeat. So until you get the one thing is, when you go to the 4th level, you'll find actually you will get the size for the 4th level is 2 to the 12 byte. Actually, 2 to the 12 byte is possible to fit in 1 patch. So we will stop here because it is enough. I mean, it is possible for you to say, okay, I cannot get more level, 5th level, 6th level. They're all possible to get. But the more level you get, the higher translation costs they are, because each time, each level, when CPU access, they will be on a DRAM. So each time will be 1 DRAM access. Okay. So 4 is the minimum number for this. Under this configuration, 4 is the minimum level for the patch tables. Okay, so this is like this. Okay, so actually our midterm will cover only till here. And then the next 3, I would say like designs, I think it is quite interesting to let you know. The first one is, so we talked a lot about like there are virtual memory, those kind of things. But have you ever think about, in terms of CPU, how to enable MMU, or how to begin the memory virtualization? Because if you still remember for the kernel, when the CPU is going to do the kernel translation, actually it doesn't really need a very complex patch table. We just add an offset, then we can get where the kernel address. But when we're running a user process, each instruction, I would say maybe not each, but most of the instructions, you need to do the address translations, and it takes a lot of time. And using this translation, you will translate to different place, and usually you cannot know beforehand, right? You need to work the patch table. So actually, when the system is boot, the MMU is inactive. So it means when the system is boot, there is no patch table, okay? So MMU is active until CPU runs a specific like instruction, okay? So the instruction is to set the CP15 register to 1. Then it will put the CPU from the physical address space to the virtual address space. Before MMU is activated, CPU only execute on the virtual physical address, because CPU doesn't really know the virtual things, okay? So like this. So this is a physical address space, and CPU will start to execute the first instruction, second instruction, as I say, right? So when CPU execute to this 0x40, this address, and CPU access this store CP15 to 1, and CP15 is the 15 core processor in Intel CPU. I mean, different kind of CPU mode will be different. Like AMD ARM, they will have different way to enable the MMU, but this is only for the CPU, the Intel CPU. So I think it is hard to image what I was saying. So I give you an example. If this is a very simple CPU and there is a cached MMU and this is a CPU, right? So enable MMU means like this. Okay. So this is an enable MMU command. So when you execute it, okay, and there is a thing called jump, because you need to think about like when you enable the MMU, then in 0x44, after this, MMU is activated. Okay. So we will use a jump command to jump to the place that where is the user program is. Okay. So because now 0x40, 0x44, they are all for like the system built-in phase, but your program, your code usually is not here. Usually they are for system built-in things. So if we are going to get where the code it is, where is your user code, we need one jump command. Okay. So with using this jump command, like this jump command 0x100 will jump to here. Okay. So because 0x100, it is also a virtual address. So using the MMU, it can be translated to the physical address. So after the translation from MMU, you can get a physical address is, hey, actually your next process is on 0x84. So the key thing is this jump command to execute your first program cannot be physical address here. It should be some virtual address. And you already know it is translated to this physical address. And then after you activate the MMU, I mean after 0x44, all of the instructions, they are virtual instructions, they are virtual memory, they are virtual address. Okay, so you should use the MMU to do the translation until CPU inactivate MMU. I mean, CPU is also possible to inactivate MMU, but at that time, what CPU see, they are all physical address. Okay, so this is quite tricky here because actually 0x100, is it a virtual address or is it a physical address? They're all possible. It depends on how CPU translate, how CPU explains this address. I mean, because here is MMU, so when you are a programmer, you should know this will be a virtual address. But I mean, if there is not MMU here, if CPU doesn't run this command and CPU directly run jump to the 0x100, then CPU will directly jump to 0x100. Okay, so in this scenario, 0x100 will be a physical address. Okay, so this is how the virtual address was the beginning of the virtual address. Okay, so the second one is about the inverted patch table. So system needs a large memory space to store multi-level patch tables, right? Because each level you need to store their patch table entry and you need to store to a lot of places. It comes to a lot of memory. So there is another patch table called inverted patch table. Maybe you already learned it in your undergraduate, but I just recall it for you. So inverted patch table usually it is a single level patch table. And the PD is quite simple. The process ID, patch number, and offset. So with this information, you can finish the inverted patch table. So like this. So process ID and patch dash number equals the function of multi-level tables. Because it directly write into their patch table entry. So if you still remember in the multi-level patch table, actually there is no process ID here because each process has their own patch table, right? So the different thing is for inverted patch table, there is no multiple label here. So it is not possible to store like for each process they have their own patch table. So all the process here they share the same patch table. But like we need some way to identify, oh, okay, this is for process 1, that is for process 2. Okay, so they share the patch table. Okay, So if a match is found, that means, okay, process one is going to access its first patch. Then we can get the physical patch by I offset. Oh, sorry. I think this I should be this I. That should be the same. Okay. So with this one, actually you can directly do the translation. It's quite simple. Just like you can check the first one, second one, the third one. And then if it is the fifth one, the PIDP, and then you can directly say, okay, the physical address is on the fifth location, and you can get an offset and you can write it. Okay. So this one is because all the process they share this patch table. So if you sort the physical address by if you store the physical address, then you can assign the physical address to each request. For example, process one is going to have to allocate this first patch, and then we will give it the first address of the physical address. And then process two with its first patch is going to allocate one patch, then physical address can give it the second one. And because this patch table will only go down, so each time when the process is going to get a new patch frame, we can give it in a sorted way. Okay. So this is inverted patch table. And here are several disadvantages for this design. The first one is it should walk through the whole table if there is no match. I mean, actually, it doesn't really know how many process ID there are. And you also don't know how many patches are there for each process. So this table will be super huge, but it will not be larger than the multi-table because there's only one table, and all the process share this level. So it should be smaller than the multi-table. But the thing is, there is no faster way to do the search. You save the memory, but you trade off for your performance. And the second one is only physical patch can, one physical patch cannot have two shared virtual address. The reason is the physical address is allocated according to those, like, we sort all the physical address, and if there is a request, we give the ID for the physical address out. Okay, so in this case, if there are two processes, if there are two patches, they are shared for one physical address. Actually, in this physical patch table, it cannot be happen here. Okay, because we use the index to do the physical address tagging. So no two patches or no two process can share the same physical patch. So this is the drawback for this design. But I mean, usually for this inverted patch table, they can be used in the embedded system, because for embedded system, if there's only one process or like two processes and there are not much of patches, then this one will be super step. I mean, it doesn't really need too much of memory. And usually for embedded, if they're not using this kind of share, like one physical patch shared by two virtual address, then it is a good fit for it. Okay. So the third one is like the huge patch. I think maybe we can take a 10 and then come back later. Okay.